Okay, for warm-up 1, we're given a polar point. We're just asked to convert it into xy. So I'm just going to use r cosine theta, r sine theta. So I get r cosine 2 pi over 3, and then r sine 2 pi over 3. So let's just evaluate this. Cosine of 2 pi over 3 is going to be negative 1/2. Sine is going to be a positive square root of 3 over 2. So I end up with a negative 3/2, comma 3 rad 3 over 2. Done. 2, we're given a rectangular point. We're asked to find some polar coordinates that give us angles between 0 and 2 pi. So I personally think it's easiest to always graph this stuff. So when I graph this, I can recognize right away what the radius is. It's 3 rad 2. I know what the reference angle is. It's 45. So I'm going to use positive radius and positive angle. So that's going to be 7 pi over 4. And then I can use a negative radius with this angle over here, so that's going to be 3 pi over 4. And both of these will meet the criteria of being between 0 and 2 pi. 3a and b, we're given rectangular equations. We want to just convert them into polar. So this one's actually, they're both relatively easy. We have x squared plus y squared. That's just r squared equals 25. So when I take the square root of both sides, I get plus or minus 5. So it doesn't really matter which one of these ones we use, r equals 5 or r equals negative 5. And let's think about these real quick. What are these actually going to give us? If we were to graph things that have a radius of 5, do we care what the angle is? If there's no theta, we don't. So these are just going to give us perfect circles with a radius of 5. And if it was negative 5, instead of starting here, it would have just started here and gone this way. So they both give us the same exact done equation, just kind of starting in different areas. Y equals x is going to be similar. We can just use the formulas. We'll have r sine theta equals r cosine theta. So immediately the r's cancel, so we're left with just sine theta equals cosine theta. I can divide cosine to the other side. I'll get tangent theta equals 1. We could leave it this way, but most people go one step past this, which is to actually find the angles. So this is going to be theta equals either pi over 4, or we could have theta equals 5 pi over 4. And let's think about that. Theta equals pi over 4 is going to be right here. And since we aren't given a radius, that means it's all radiuses. So that ends up filling in this entire line in both directions, which is y equals x. All right, we're going to try out this camera angle for a little bit here. Let's start off with r equals 4 and try to see what this will become. So if I have a radius of 4, it doesn't say anything about theta. That means theta can be anything. So I'm just going to say, okay, well, what if theta was 0? I'd be 1, 2, 3, 4. I could have a point here. What if theta was 15 or 30 or 45 or 60 or any of these points over here? So what we end up with is a circle with a radius of 4 centered at 0, 0. So this equation, r equals 4, this gives us a circle. I'm not sure how easy that is to see, so I got us this backup marker that will hopefully be a little bit easier to see on that camera. Can we pretend like that was actually a circle? That was good enough, right? Next we have r equals 5 cosine theta. So in order for us to do this, let's actually plot some points. So if cosine of 0, that's 1, so I'm going to have 1, 2, 3, 4, 5. I'll have a point out here. And let's see, what would be another good one? Cosine of 60, that's going to be 1/2. So I know that when we're at 60, which is right here, this is going to be 5 times 1/2. It's going to be at 2.5. And at 90, cosine of 90 is 0, I'm going to be right here at 0. Okay. And if I were to plug in a couple other points here, like for example, if I plugged in 2 pi over 3, it would be a negative. So that's going to be down here at negative 2.5. And so forth. If I continue to plug in additional points, what we would see is that this creates a circle, pretend like that's a circle, please, a circle that's centered around the x-axis, which should kind of make sense, right? Cosine is really an x value, so this is really a circle that wraps itself around the x-axis. And that 5 there, that's our 1, 2, 3, 4, 5, that's what the diameter is. So that's pretty neat. Okay, next we have r equals 3 sine theta. So let's do the same idea. Let's plug in some points. If I plug in 0, sine of 0 is 0, so I'm going to be right here. If I did sine of 30, that's a half, so this is going to be at 3 times 1/2, so 3 halves, which is going to be right there. And let's see, 60 is not nice, 45 is not nice, 90 is going to be 1, so this is going to be 1, 2, 3. If I do 150 over here, sine of 150 is positive, so it will be right here, and then we'll end up back here. So if I had connected or drawn a bunch more points in here, this ends up making a perfect circle. And again, let's pretend like that's a circle. This time it's focused around the y-axis, and that should make sense because sine is y, and we have a diameter of 3. So I hope you're able to make some of the connections between these ones here, right? If we have a number cosine theta, that's going to be wrapped around the x-axis with the diameter of that number. If a number sine, that's going to wrap around the y-axis and going in that direction. If we have one that's just r equals, that's going to be a perfect circle centered on the origin. Next we have lines. We'll start off with one that I think we've actually kind of done before, but we have theta equals pi over 4. So here is pi over 4. I'm just going to mark it with a little dashed line real quick. And there are no r values here, which means r can be anything. So let's say r is 0, I'm right here. If r is 1, I'm right there. If it's 2, if it's 3, if it's 4, if it's 5, if it's negative, it goes this way. And what we end up with is every possible point along this line here. So theta equaling a number, that just creates a line through the pole, so through the origin, at whatever that angle is. For r equals 3 cosine theta, we've actually done this by solving them before, so putting it back in rectangular. So I'm going to continue doing that. I'm going to do r cosine theta equals 3. I know that r cosine is really an x value, so this is really x equals 3. So that's super easy to graph. X equals 3 is a vertical line at 3. Done. Last but not least, we have r equals 4 over sine theta. We can do the same thing, multiply the sine theta to the other side. And r sine theta is really y. So this is really y equals 4. So 1, 2, 3, 4. It's going to be a horizontal line right here at y equals 4. So to kind of summarize here, we have these two main cases, a number over cosine or a number over sine. Those are both going to be lines, depending if it's cosine or sine, whether it's vertical or horizontal. And if we have theta equal to a number, that's going to be a line through the pole, extending infinitely. Next, we have spirals. So this is r equals theta, and we're definitely doing this in radians. Okay, so I'm going to start off with if r equals theta directly. So if theta is 0, then the radius is 0. That was easy. If, let's say theta is pi over 2, so pi over 2, that's like a, basically 3 over 2, give or take. So that's going to be at 1/2. So I did pi over 2 as the angle and out pi over 2. When I'm at pi, r is going to equal pi, so that's going to be a little bit bigger than 3. When I'm down here at 3 pi over 2, that's really like 9 over 2, so that's going to end up being somewhere around 4.5-ish. And when I'm all the way back over here at 2 pi, then that's going to be like 6.28, so that'll be somewhere out here. So what this does is it creates this spiral effect, because as theta increases, so does r. And I do want to point out here that I am very specifically doing theta is greater than or equal to 0 right now. And let's think about what direction that went. That went counterclockwise. So it's kind of neat. If we did theta less than 0, so we plotted these ones, it would actually do something pretty neat and interesting. So if I were to do this, so I'd still get 0, 0, but now if I went negative pi over 2 as my angle, it's actually going to reflect up here. So that would be my first point. When I'm at negative pi, a radius that's negative is going to go in the opposite direction, so it's going to be over here. When I'm at negative 3 pi over 2, that's going to go back down here. And then when I'm at negative 2 pi, that's going to graph way over here. So it actually spirals like this. So together they make this kind of really cool shape, and if we increased the angle, you could see even more. I might suggest that you put your calculator into polar form and try graphing some of these, and you'll see what they are. But when theta is negative, it creates one going clockwise. If we have r equals negative 2 theta going on here, let's again plug in some values. If theta equals 0, then this is going to be 0. If theta equaled pi over 2 times a negative 2, that's going to be negative pi. So instead of graphing here, it's going to be graphing down here, 3 radius of pi away. When I'm at pi, I'm going to be at negative 2 pi, so that's going to graph over here. So what's interesting about this is that it still graphs in the counterclockwise direction. It just actually goes much faster. So the spiral will actually open up over a much longer period of time. But the negative doesn't actually do anything other than instead of starting over here in quadrant 1, it actually starts in quadrant 3. So whereas this red one started into quadrant 1, this one actually starts into quadrant 3. Last but not least for the spirals, we got this one, theta over 2. So if theta equals 0, we'll be at 0. If we're over here, pi over 2, that's going to end up giving us a radius of pi over 4. So that's like basically like 3/4. So that's going to be right here. If we're at pi over 2, that's going to be at like 1.5. If we're down here, 3 pi over 2, that's going to give us like 3 pi over 4. So that's going to be like a little bit bigger than 2, I think. When I'm over here at 2 pi, that's going to end up just being at pi. So 1, 2, 3. And we could keep going. As we continue around, we'll get more and more points here. I think I've run out of room if I go past that. But basically what happens here is the spiral, we get more of it because we're decreasing the radius by dividing by 2, the angle divided by 2. So this one spreads out the spiral. This one makes the spiral shrink in on itself. And we can make it reverse direction by using negative angles instead. All right, now we get to the big ones. We have rose curves. Okay, so these are super important ones and they make really, really cool shapes. We're gonna start off with r equals 9 cosine 2 theta. And what I actually want to do with this is just do a quick little sketch of it, okay? And I'm going to do all the way up to 2 pi. So my period of cosine is normally 2 pi, but we have this 2 theta here, so I'm going to divide by 2. So period's going to be pi. My x scale is always period divided by 4, so that's going to be pi over 4. So it's cosine, so it starts at the top, goes down, goes back up, goes down, goes back up. And that's going to be where 2 pi is. Okay, so I'm just going to keep labeling some of these things here. There we go. Let's try to figure out where each one of these pieces are right here and use those to help us start this graph. So obviously that's at an angle of 0. This is going to be pi over 4. This will be at pi over 2. Now notice it's a negative radius. That's important. This will be 3 pi over 4. This will be at pi with positive radius. Let's see, 5 pi over 4, 6 pi over 4, so this is 3 pi over 2, 7 pi over 4, and back at 2 pi. So I'm going to graph this in the blue marker, or the blue pen, and then I'll add some color to it. So if I start off here, and this is with a radius of 9, so I'm going to increase myself all the way out to here, and I should have used the other scale, but 1, 2, 3, 4, 5, 6, 7, 8, 9, so I'm going to put a point right here. Then I'm going to go to pi over 2, but it's a negative radius. So instead of graphing here, it's actually going to graph down here. Okay? So if I start off by looking at this, we start off at a maximum radius, and then at some point we hit 0 by the time we get to right here, pi over 4. So I know that this goes like this, and it's kind of getting smaller as it gets in with the angles. Now, from pi over 4 to pi over 2, it's a negative radius. So it's actually going to be graphing over here. Okay, and it's going to swing out until it hits this maximum at pi over 2, and then as we go from pi over 2 to 3 pi over 4, we're still negative, so it's going to be actually graphing in quadrant 4 over here. Once we hit 0 right here, then it's back to being positive. So from 3 pi over 4 to pi, we're in this quadrant until we reach the maximum at 9 at pi. Then we're going to be swooping back down into 0. Now, once we reach here, which is 5 pi over 4 until 3 pi over 2, actually all the way until here, we have negative radiuses. So we're actually going to be graphing in the opposite quadrants. So from here to here, we'll actually be in quadrant 1 until we loop up and hit negative 9 at 3 pi over 2. So it reflects, and then it comes back. Now from here to here, we're actually in quadrant 4, so it goes like that. So this graph over here tells us exactly what quadrant we're in based on the angle and what the radius is. So this very first part right here, this is in quadrant 1. This part right here, if we split this in half, it was down here in quadrant 3. and then it went to quadrant 4 to complete that part of the petal. Then we went over here into quadrant 2, followed by quadrant 3. Then we went into, let's see, the opposite quadrant. So this is right here, quadrant 1, and then quadrant 2. That got messy, my apologies there. And this is in quadrant 4. So by knowing this graph, we know where this one is based on the theta values. Let's do the same exact thing. This time we'll have r equals 9 sine 2 theta. So when I go to graph this one, same idea. Our period is normally 2 pi over 2, so it's going to be pi. Our x scale is going to be pi over 4. I want to graph this all the way to 2 pi. So when I do this, okay, it's sine, so I'm going to go from here. That's going to be to pi, and I will continue one more time here. Now I'm hoping you recognized from this one that we kind of had a half petal here, 1, 2, 3, and a half petal here. So that made 4 complete petals. So if we're looking at this, my guess is we're going to have 4 complete petals. And just like last time, I want to find where these maximum ones are. So it started at 0, then we have pi over 4. This is going to be at pi over 2. This will be at 3 pi over 4 with a negative radius. Pi, 5 pi over 4. 3 pi over 2, this will be 7 pi over 4 with a negative radius, and that's our 2 pi. So I'm going to start by plotting those maximums. So at pi over 4, we're all the way out here at a maximum of 9. 3 pi over 4, we're actually negative, so it's going to be down here. Okay. And at 5 pi over 4, we're in that direction because it's positive radius. And 7 pi over 4 will actually be the opposite, will be out here. So let's label some of these extra things in here. Those were maybe important for us to know what they were when we're talking about things. So from 0 to pi over 2, we have all of these things are in quadrant 1 with a positive radius. So we have this petal that goes out like this. It's probably a little bit fatter. I'm not that super accurate of a drawer when it comes to these things, but we go all the way out. Here we have angles between pi over 2 and pi. So the angles are in quadrant 2, but we have a negative radius. So this is actually going to be in quadrant 4. Next we have between pi and 3 pi over 2, so those are angles in quadrant 3 with a positive radius. We will stay in quadrant 3, so it graphs this part next. From 3 pi over 2 to 2 pi, those angles are in quadrant 4, but the radius is negative, so it's going to graph itself over here. So this is a complete graph. Now let's just compare these two really quickly. We can see that the cosine graph started over here, wrapped itself around the x-axis. The sine graph did not. It kind of wrapped itself over here first. When we had 2 theta, we had 1, 2, 3, 4 petals, so that's important for us. And I think this is a good time for us to figure out the shortcut rather than waiting. Normally we would wait. So when we're looking at this, whatever is in here, if this value is even, so we normally call that k, so if k is even, then we're going to have twice as many petals as it says there. So in this case, it's 2, so we're going to have 2k petals, so 4 in this case. Now to figure out some other things, once we know how many petals there are, we like to find the angle in between them. So I know that there's 4 petals, and they're going to go all the way 360 around. So I do 360 divided by the number of petals. In this case, it's going to be 90. So once I know where one of them is, I know that they're all 90 apart, and that works for both of these ones. So some other things we need to figure out is the maximum radius. It's always just this number right here, which is commonly referred to as A. So that brings us to the start. And start is tricky. It's not really tricky, but basically what we do is for cosine, we need to know when does cosine have its first maximum. So cosine has its first maximum at 0. So we basically say that 2 theta equals 0, and this is going to be where the first max is, whatever that solves to be, which for cosine always happens to be 0, which we got right there. For sine, its first maximum in like traditional sine world happens at pi over 2. So what we do is take 2 theta and set that equal to pi over 2 and solve for theta. That's going to be pi over 4. And we know then that the first max happens at pi over 4. So if we know the first max and we know the angles in between, then we can solve where all of them are without needing to actually do this part of the graph. Pretty neat, right? 2 more left. We'll see if they follow the pattern. Hint, they don't. They do, but they don't. Let's be real here. So we have a 3 in here. So this is actually different. So when we have an odd number in there, we don't need to go all the way to 2 pi. We actually can stop at pi. So if cosine traditionally has a period of 2 pi, it's now going to be 2 pi over 3 is where we're actually going to have our period for. And then our x scale is going to be, I believe that's pi over 6, okay? So I'm going to graph 1.5 of these. And I know it's 1.5 because I know it's going to be pi, but let's just confirm. Here's pi over 6. This will be pi over 3. This will be pi over 2. This will be 2 pi over 3. This will be 5 pi over 6. And this will be 6 pi over 6, or pi. And what this is going to create is 3 petals. Here's a half petal, here's a full one, and another half one. If we come over here and try to graph these, we're going to have one at 9. Our next maximum is at the angle of pi over 3, but it's a negative radius, so it's actually going to graph over here. Then we have 2 pi over 3, so that's up here. It will be in that direction. And then at pi, it's negative, so we end up back here. So this graph goes like this. It starts off in quadrant 1. Then it loops down into quadrant 3 because of the negative radius. Then it loops up into quadrant 2. And then it ends up in quadrant 4. So if I label that over here, we have Q1. We're going to be this entire thing actually in Q3. Didn't need to break that one up. This entire one is in Q2. And this part right here is in Q4. And I'm just looking at the angles and whether they're positive or negative radius to tell me whether I stay where that angle is or go the opposite way. Let's see if our shortcuts work for this one. We do have to change some things up here. This time our K value is odd. So whenever it's odd, that's equal to the number of petals, okay? So we have 3 petals here. Once we know that, we can find the angle in between the petals by doing 360 divided by that number of petals. So that's going to be 120. So each one of these is 120 away from each other. We know the max R is going to be 9. It's always that number right there. So we just need to figure out the start. And this holds true. We have 3 theta equals 0, and that's because we have cosine here. And theta is going to equal 0. So our first maximum occurs at 0, and the next ones are 120 apart from that. So we didn't really need this. This is useful later on, especially in calculus for you BC folks. Last one, we have r equals 9 sine 5 theta. And I think what I'm going to do is just use these shortcuts for this one rather than the real way. So I'm going to start off with identifying my max radius is 9. My number of petals is going to be, it's odd, so it's going to be equal to that, 5. That means that the angle in between all of them is 360 divided by 5, so I'm pretty sure that's 72 degrees. And you need to know where the first max is. So I'm going to do 5 theta equals, and I'm going to do it in degrees just to make my life a little bit easier here. So sine's first one is normally at 90, so I'm going to do 90 degrees. So theta is going to equal 90 over 5, and I'm pretty sure that's 18 degrees. So the first one is at 18 degrees. That's annoying to try to plot. I'm going to use the red marker here. Let's see, this is 15, so 18 is going to be a little bit out there. Then I just have to add 72. That's going to be at 90. Add 72. That's going to be somewhere like right here-ish. Add 72 to whatever that number is, and that's going to be somewhere. I got to think about that. I think it's like right here, and then it's going to be right here. So this one is going to go, actually goes like this, its graph. It's pretty crazy. It goes like that is the order that it actually follows. So this one has 5 petals. Each one is 72 away. The first one starts at 18 degrees.